Hello student friends, I'm putting some lectures on electrostatics. It will be a series of lectures. The first lecture will be on electric field. So I'm putting my first video on this electric field. Okay, fine. Then let me first talk about what is electricity actually. It's a study of one part of physics where we study about the charges. The charges may be at rest or may be moving. If it is at rest, then we call it electrostatics, and if it is moving, then we call it current electricity. So deal with charges whenever we talk about electrostatics or current electricity. The basic law in the electrostatic is Coulomb's law. So being presented here, which is a vector, is in vector form. F equal to K capital Q small q divided by R square, with R cap being the unit vector. The R cap unit vector is actually representing the direction of F, as F is a vector quantity, force is a vector quantity. So with this very idea, let's now proceed to define electric field actually. There are two ways, one is qualitative and the second one is quantitative. Both the definitions are very useful. The first definition, that is qualitative definition, is that if we take a charge, that charge has some effect and there is a region of space where up to which we can feel that effect. And that particular region up to which we can feel the effect of the charge is known as electric field. So qualitatively, we think field as the region of space up to which the charge can put its effect. But the important thing is that we need a quantitative definition as well, as defined here. And in that case, we take two charges. One is the original charges whose electric field is to be calculated, and the next charge is the test charge actually. And so here in the expression here, we are showing the electric field. Thing is that we use the Coulomb's law for defining the electric field. If we, as in the last slide, we see that force between two charges are capital Q small q by R square, whereas the distance between them. Now the same idea is used here. Only thing is that we put Q equal to plus 1. That means it is a unit positive charge, and we treat that small q charge as test charge. So with that test charge, that means if Q is equal to 1 plus 1, then that force becomes electric field, and that's why we write like this, F by Q. So F by Q is equal to, from that expression, K Q by R square. Of course, that K is equal to 1 for CJ system and 1 by 4 pi epsilon not for MK system. So with this expression, we can now try to find the electric field in a more elaborate way. We first start with taking that figure 1.1. We see that capital Q charge at the origin of a coordinate system, and we are bringing that charge Q, which will be taken at unit positive charge here, and R is the distance. And as we know from Coulomb's law, the force is this, and the field is like this. We put a limit here, Q tends to 0, which means that the effect of this test charge Q is infinitely small. It is infinitely small in the sense that it does not affect the field created by capital Q. So that's condition that one must preserve. Next, if the original charge capital Q, whose electric field we are calculating, is not at the origin, is somewhere at the point A, say, and that unit positive charge at point P. In that case, we take the diagram 1.2, and we see that that R is the position vector of capital Q, and R dash is that of small q. And they have varying distances, capital R and capital R dash. Small r and small r dash, they are in vector form, and the distance between A and P is this R minus R dash. They are vectors, and in that sense, using Coulomb's law again, we get like this: R minus R dash squared. Now we can see that this R is coming, and this R cap is again meaning that direction of the force, since Coulomb's law is a vector law. Now we can put this in this form also. Like when this cube term comes, that R cap goes and this R minus R dash comes. They are vectors. So in the sense that in the same way, that's putting that we're dividing the thing like this. I think it's a small q and f by small q, and it will give you a task like this. If you take this form, it is capital Q, r minus r dash square, and this r cap is unit vector. And if you take this vectorial form of this r cap, then that is like this. So we are having two forms of electric field if the capital Q charge is at the origin, and that is this form when the capital Q is at the origin, and this form when capital Q is not at the origin. Now the point about electric field, that is conservative nature. The electric field being conservative, and it's conservative from the conception that if you take curl of it, then it becomes zero. So it's a very basic definition of conservative field, that if the curl of a field is zero, then it's automatically means it's a conservative field. So electric field is conservative field, and we can check that also, that curl of is equal to zero. Now another important point is that the curl of field is zero. That means that the curl or the electric field actually is some gradient, actually negative gradient of some function, some scalar function, and that scalar function is actually nothing but electric potential, which we'll take care of that in later course of time. So thing is that E is conservative field, curl of E is zero, and as well as E is some negative gradient of some scalar function known as. So coming back to the point how to prove curl E equal to zero, you can see we start from the very first from the expression for electric field, that is equal to k q by r square, okay, as shown, and we find out the curl of E. So doing this, we put all this k is constant, capital Q is constant. The only thing is that you can put them outside of the thing, and this is curl of r vector by magnitude r cube. Magnitude r cube. Okay. But from mathematical identity, vector identity, this curl of r by r cube can be put like this, and then get gradient of 1 by r cube cross r, 1 by r cube, and then this curl of r. So curl of r is 0 because r is, we can prove it, curl of r is 0, so that put 0, and then this result of this gradient of 1 by r cube is minus tr by r cube of 5. So we see that there are two vectors, r and r. Since two vectors are parallel, or same vectors in vector identity, if two vectors are same, they are parallel, and that means parallel vectors, when we take the cross product, it gives 0. So this r cross r also gives 0, as well as this is already 0, so 0 0. So ultimately curl of E is equal to 0. So this certainly proves our point that curl of E is equal to 0, and that's how we can prove that electric field is conservative nature. So to conclude that electric field can be defined in two ways, qualitative as well as quantitative. Qualitative means that we can see it in a physical form, how physical relation it can make it, and the quantitative means just like the expressions, that how we can mathematically represent it. And then we can also, one of the basic property of electric field, that is that curl of it vanishes, which means that it's a conservative field, as well as it can be a gradient of some scalar function. We will find it later on that this is nothing but it's a gradient, actually negative gradient of electric potential or electric field. So to conclude, we put some assessment. The electric field for a point charge, you can consider both the origin at origin or at some other point. Also some component in terms of x, y, z. That means r is equal to I cap x plus j cap y plus k cap y. We can put like this. And capital E can be, or the, vector E can be written like I cap EX plus J cap EY plus K cap EZ. And then question number 3, why electric field is conservative? We can just already shown it, and that is also why the negative sign is there between the electric potential and field. So we choose this question because in the 10+2 course, basically these questions are there, and so to refresh your memory, you can put like this, and the elective, and then how to prove it like this. So I think that the answers are here already there. So going through the video, you can find it all around the answers. Thank you very much for watching the video. Hope the video is useful for you. Thank you once more.